What if the universe isn't a collection of separate things, but a single, endless ocean of invisible energy, rippling everywhere, all the time? Most of us go through life seeing solid objects, tables, phones, cars, even planets, as the main players in reality. We imagine them as hard little blocks, floating through empty space, bumping into each other, doing their thing. But what if that's just an illusion, a story we tell because our senses can't pick up the real truth? The real story is so strange, so beautiful, that it almost sounds like poetry or science fiction. Everything you see and touch is just a ripple in a field that stretches everywhere. So let's play with this idea. Picture yourself at a quiet lake early in the morning. The water is so smooth it looks like glass, perfectly still, no waves, no movement. Now, you pick up a stone and gently toss it into the water. Instantly, the surface comes alive with ripples spreading out in perfect circles, growing, touching the shore, then fading away. Those ripples are not objects themselves. They're just patterns moving across the water. Now, imagine that this is what the entire universe is like. The stone, the ripples, the water, even the space between everything, all are part of the same thing. A vast, ever-present field. In the world of quantum field theory, this is not just a metaphor. It's the actual foundation of reality. Instead of thinking about the universe as a giant box full of tiny marbles called particles, physicists realized that it works much better to imagine fields everywhere. Every kind of particle, electrons, photons, quarks, even the mysterious Higgs, is really just a ripple or a wave in its own field. An electron is a ripple in the electron field. A photon, which is a particle of light, is a ripple in the photon field. Even when nothing seems to be happening, these fields are still there, silent and waiting, like a pond before the stone drops in. This idea changes everything. In the old days, science described objects as little dots zooming through empty space, sometimes crashing, sometimes sticking together. That works for explaining a lot of things like why billiard balls roll or why apples fall. But when scientists started exploring the tiniest, weirdest parts of the universe, things like atoms, light, and even the vacuum itself, the math just didn't work out. Strange things kept happening that nobody could explain using only particles. Sometimes light acted like a wave. Sometimes particles popped in and out of nowhere, breaking every rule. It was only when scientists imagined fields instead of objects that the puzzle pieces finally started to fit. So what is a field, really? A field is something that exists everywhere, at every point in space, always ready to be disturbed. It's invisible, but not empty. When you excite a field, add energy to it, it creates a ripple. That ripple is what we see as a particle. If you stop exciting the field, the ripple disappears, but the field is still there, waiting for the next disturbance. Imagine the universe as a giant stage with a floor made of these invisible fields. The actors, the particles, appear only when someone steps on the stage and moves. But the stage itself is always there, even if nobody is acting. It gets even wilder. All the different fields, electron, photon, quark, Higgs, are layered on top of each other, occupying the same space. Right here, where you're sitting, there are dozens of fields filling the room, even if you can't see or feel them directly. They interact and overlap, sometimes mixing together, sometimes staying apart. When you see a flash of light or feel a warm breeze, what's really happening is that one field is vibrating, passing its energy along, causing other fields to respond. You're not a thing made of things. You're a pattern of vibrations moving through the fields, a unique song playing in the universe's endless symphony. Now, let's zoom in and try to see what's really happening at the smallest level. If you take a microscope and look at your hand, you'd see cells. Zoom in further, you'd see atoms. Go even deeper, you'd see electrons, protons, neutrons. But go even further, beyond the atoms and into the heart of quantum land, and the solid, simple picture vanishes. There are no tiny marbles. There are only fuzzy regions where the fields are more excited, places where the energy of the universe's blanket is rippling just enough for you to notice. Particles can appear as dots on a screen, sure, but before they show up, they exist as a blur, a wave, a probability, a suggestion more than a solid object. The field tells the universe where the dot might land, but it's the field itself that's real. There are no clear borders, no edges, just overlapping patterns of vibration. Here's something even stranger. What we call empty space is not empty at all. The fields are still there, quietly buzzing, even when nothing seems to be happening. The vacuum, in this view, is like the world's quietest orchestra, playing silent notes that sometimes get loud enough to be heard. Even in a perfect vacuum, the fields can ripple and produce particles for a split second before disappearing again. Nothingness, it turns out, is full of potential. All of this can sound pretty abstract, but it matters more than you might think, because it means you are not made of little blocks glued together into a statue. You are a living pattern in a sea of invisible energy, always in motion, always changing. Even your thoughts, your feelings, your memories are possible only because the universe is alive with these fields. When you think, when you move, when you dream, you're really stirring up the fields that fill all of reality. If you could see the world through the eyes of quantum field theory, you'd see everything shimmer and blend together. You'd notice that there is no sharp line between you and the rest of the world. The air, the sunlight, the ground, your very self, all are waves on the same endless ocean, sometimes rising up, sometimes fading back in, always connected. This is the universe's secret language. It's a language written not in words, but in ripples. A language that says there are no things, only actions, no nouns, only verbs, no fixed objects, only endless, beautiful change. It's the reason why everything you know exists, and the reason why everything is connected. And this is just the beginning. In the chapters ahead, we'll dive deeper into how these fields interact, how they create the forces of nature, and how understanding them could unlock even more secrets about the universe and ourselves. So next time you look at your hand or gaze up at the stars, remember, you're seeing ripples in a cosmic field, part of a conversation that began long before you and will continue long after. Welcome to the real universe. Are you ready to learn its language? Imagine being told that nothingness doesn't exist, that even when you stare into what looks like pure emptiness, space between the stars, a dark corner of your room, the vacuum left after sucking every last atom out, there's actually something buzzing, humming, waiting. This isn't a metaphor. It's real, and it's one of the wildest, most important discoveries in all of science. The universe, at its deepest level, is crowded with invisible fields, even where you think there's nothing. Let's take a closer look at what this really means. If you could somehow shrink yourself down smaller and smaller until you're standing in the space between two atoms, you might expect to find pure emptiness. No particles, no light, just a vast blackness. But quantum field theory says otherwise. Every spot in the universe, even in the darkest, coldest vacuum, is home to a whole family of fields. There's an electron field, a photon field, a field for every known particle, even a mysterious Higgs field that gives things their mass. These fields aren't rare. They're everywhere, always present, like invisible wallpaper covering reality. Think of it like this. Instead of being surrounded by air, imagine you're swimming in an ocean of invisible jelly. This jelly fills every room, every corner of space, every gap inside your body. You can't see it or feel it directly, but it's always there. And every now and then, a ripple moves through this jelly, a little vibration, a disturbance, and that's what we call a particle. If the electron field ripples, you see an electron. If the photon field shakes, you see a particle of light. But what about empty space? Shouldn't it be quiet and still with the fields at rest? Here's where things get truly bizarre. Even in the most perfect vacuum scientists can create, the fields don't just sit quietly. They can never be completely calm. Instead, they're always jittering, like water that never settles. Tiny fluctuations constantly pop in and out of existence, creating little bursts of energy. These fluctuations are built into the rules of quantum mechanics. Nature never lets anything stand perfectly still, not even for a split second. It's like the universe has stage fright, always fidgeting, never quite able to relax. This hidden activity has real effects. Imagine two metal plates in a vacuum placed close together. You'd expect nothing much to happen between them. But if you wait and measure carefully, you'll see a mysterious force push the plates together, as if the vacuum itself is doing the squeezing. This isn't magic. It's called the Casimir effect. What's happening is that the fields between the plates can't vibrate as freely as those outside, and this difference creates a gentle push. This invisible pressure from the vacuum is so real that scientists can measure it in the lab, and it matches the predictions of quantum field theory exactly. It's not just empty space that's filled with fields. Every object you can see is built from overlapping fields, stacked on top of each other like layers in a cake. The air around you is a playground for the photon field and the electron field. The ground beneath your feet is made from the same fields, just vibrating in a more organized way. Even inside your body, fields are weaving in and out, giving rise to every cell, every atom, every spark of thought. The fields aren't separate. They blend and interact in ways that create all the richness of the universe. You might be wondering, if these fields are everywhere, why don't we notice them? The answer is that most of the time, they're in their lowest energy state, what physicists call the vacuum state. It's like a crowd of people all standing quietly in a dark room, barely moving. But every so often, something disturbs the calm. Maybe energy is added, or a particle smashes into something. Suddenly, the field ripples, a particle appears, and the universe comes alive. The calm isn't emptiness. It's potential, always ready to erupt into something more. This is a totally new way to think about reality. The world isn't made of stuff floating in nothingness. Instead, there is no true nothing. There's only fields, energy, potential, readiness stretching everywhere. Particles aren't little dots flying around in the void. They're the visible peaks of invisible waves, temporary patterns that appear and vanish, but the fields never leave. It gets even stranger. Fields can interact, blend, and talk to each other. When you shine a flashlight, you're stirring up the photon field, creating a cascade of light particles. But those photons can also nudge the electron field, causing electrons to move, which is how electricity works. The fields aren't just separate teams. They're like dancers on a crowded floor, each with their own steps but constantly bumping and spinning with the others. Sometimes, fields can even mix, like in the case of the Higgs field, which changes the way other fields behave and gives particles their mass. Imagine trying to play every note on a piano at once, but instead of clashing, the notes blend into a beautiful, complex chord. That's what the universe's fields are doing all the time. They overlap, harmonize, and sometimes clash, creating all the things we see. From a snowflake to a supernova, from a human heart to the rings of Saturn. The fields make the world rich, strange, and alive. This picture is hard to accept at first because it's so different from how our eyes and hands experience the world. But the evidence is everywhere. In the lab, when scientists smash particles together or create extreme conditions, they see the fields reveal themselves. Particles blink into and out of existence, sometimes lasting for less than a heartbeat, but always following the rules of the fields they belong to. Even the empty parts of space, between stars or inside atoms, turn out to be busy with silent, invisible action. So next time you see a beam of sunlight or feel the wind on your face, remember what's really happening. The warmth you feel is the photon field vibrating in just the right way. The colors you see are the electron field interacting with photons, bouncing and shifting to create the world's beauty. The space between your fingers isn't empty. It's alive with fields, quietly humming, always ready to show you another wonder. Quantum field theory asks us to see the world with new eyes, not as a collection of things, separated by emptiness, but as a single, connected reality where nothing is ever truly alone, and every point in space is full of promise. The universe's alphabet isn't written in letters or particles, but in endless, dancing fields, each telling its own story, all at once. This is the new language of the cosmos, a language of potential, of vibration, of infinite possibility. To learn it is to discover that nothing is ever really empty, and that even the quietest moments of reality are filled with secrets. The fields are always there, whispering in the silence, ready for someone to listen. And this is only the start. Ahead, we'll see how these fields not only fill space, but also weave together the forces that move the stars, the planets, and even you. The fields are the universe's secret language, and with every new idea, you're learning to read its words. Are you ready to go deeper? What makes the universe hold together? What invisible rules let everything, from sunlight to gravity, work so smoothly, even when it seems like chaos is everywhere? If you listened closely to reality, could you hear its grammar, the secret rules that allow fields to dance, forces to appear, and everything to keep its shape? Quantum field theory has an answer. It turns out the universe is held together by symmetries and hidden patterns, rules that work kind of like the grammar of a language. These rules not only make sense of everything we see, but also create the very forces that shape our world. Imagine for a moment that reality is a giant sentence and fields are the alphabet. But just having an alphabet isn't enough, you need grammar. Grammar is what makes words come together and form meaning. In the universe, this grammar is built into the symmetries that each field obeys. Symmetry doesn't mean that everything looks the same on the surface. It means the rules stay the same, no matter how you move, twist, or turn things around. If you spin around in your chair or walk to the other side of the room, the laws of physics still work the same way. That's a symmetry, and it's everywhere. These symmetries are more than just beautiful ideas. They're powerful. In fact, the deepest forces of nature, light, electromagnetism, the strong force that holds atomic nuclei together, actually emerge from the symmetries of quantum fields. When you write out the math describing a field, and you demand that the rules are the same in every spot, at every moment, and for every angle, something magical happens. The equations tell you that certain kinds of fields must exist, and those fields turn out to be the forces of nature. Let's make it more concrete. Take the electron field. If you twist the phase of that field, a kind of hidden angle that every quantum field has, the field's behavior doesn't change as long as you do it everywhere at once. That's a symmetry. But what if you let the phase twist a little differently in every part of space? Suddenly, the math cries out for help. The only way to keep the laws of nature consistent is to introduce another field, one that can correct for all these little twists. That field is the electromagnetic field, and its particle, the photon, is the messenger of light. Every time you flip on a lamp or use your phone, you're witnessing the universe's grammar in action. Symmetry giving rise to light. The story doesn't stop there. Inside every atom, quarks are held tightly together by the strong force. The symmetry here is even more subtle, like the difference between swapping colors in a complicated pattern. Quarks come in 3 colors, not red, green, and blue as we know them, but as a mathematical property. When the rules demand that the equations work no matter how these colors are shuffled, a new set of fields must appear to keep things consistent. These fields are carried by particles called gluons, which glue the quarks together with incredible strength, making sure that the building blocks of matter never fall apart. Even the weak force responsible for radioactive decay and the energy that powers the sun comes from a symmetry, one that isn't as easy to see, but is just as real. Sometimes this symmetry breaks, and that breaking is what allows particles to change from one kind to another. It's like a sentence that can shift its meaning halfway through, letting one word fade out and another take its place. All these forces, light, strong, weak, are different, but they all emerge from one idea: that the universe's rules must stay the same, no matter where or when you look. Every time you use electricity, see color, or even just stand on the ground, you're experiencing the power of symmetry in action. The grammar of the universe doesn't just shape what's possible. It actually brings the forces to life. But there's another layer to this story, one that's even stranger. In the quantum world, the rules don't just apply to what's there, but to what could be. Because of the uncertainty built into quantum mechanics, fields can never be completely pinned down. They're always slightly unsure, a little fuzzy, and this fuzziness allows them to interact in surprising ways. Sometimes, the rules that protect symmetry let fields interact and swap energy, creating new particles or annihilating old ones, always following the cosmic grammar. Think of a dance where each step follows the beat, but the dancers can improvise within the rules. If they improvise too wildly, the dance falls apart. But if they follow the hidden grammar, the dance can go on forever, never losing its shape. Quantum field theory says the universe works the same way. Fields can ripple, interact, merge, or split, but only if they keep to the rules set by their symmetries. This idea, while simple in spirit, leads to predictions so accurate that they boggle the mind. Physicists can use the symmetries of quantum fields to calculate how electrons move in atoms, how light bounces off mirrors, how particles decay inside the sun, and their answers match experiments to more decimal places than almost any other scientific theory. The universe's grammar is strict, but it allows for an infinite variety of sentences, each one a new event, a new possibility. You might wonder, if the rules are so strict, why isn't the universe boring and predictable? The answer is that the rules are like the rails of a roller coaster. They guide the ride, keep you from flying off into chaos, but within them, there's room for loops, twists, and turns. Quantum surprises, unexpected combinations, and new forms of matter. The fields and their symmetries are both the path and the permission for everything that happens. Sometimes these symmetries break or change. When that happens, the universe gets even more interesting. New kinds of particles can appear, new forces can emerge, and the old rules might blend into something unexpected. This is how the early universe changed as it cooled down after the Big Bang. The symmetries of the quantum fields broke in different ways, giving rise to the forces we know now. It's as if the language of the universe evolved, adding new words and new grammar rules as the story unfolded. All of this means that, at the deepest level, the universe is not a random jumble of things. It's an organized conversation, a dialogue between fields, guided by symmetries that make sense of everything. Every force you feel, every light you see, every atom in your body is following the grammar of quantum fields, written into the structure of reality itself. So the next time you flip a light switch, or look at the colors in a rainbow, or think about the sun burning bright millions of miles away, remember, you're seeing the universe's grammar in action. The fields are dancing, following their rules, creating forces and energy out of pure symmetry. The language is deep and beautiful, hidden beneath everything, waiting for you to learn to listen. And as we keep going, you'll see how this grammar not only explains the forces we know, but opens the door to even more mysterious possibilities, forces and particles we haven't yet discovered, and maybe, just maybe, the ultimate secrets behind everything. The universe is speaking. Quantum field theory is the key to understanding its secret language. Are you ready for the next sentence? Imagine you're sitting in a quiet room. Nothing is moving. You might think everything is calm, silent, and perfectly still. But quantum field theory says, look again. Beneath that silence, reality is buzzing with hidden activity. The emptier things look, the more alive they secretly are. There is a secret crowd, a restless dance, happening right beneath your nose, even in what we usually call nothing. In this strange world, particles can appear out of nowhere and disappear just as fast. These are the universe's virtual particles, the punctuation marks and pauses in the universe's never-ending story. Let's try to picture what nothing means. For centuries, philosophers and scientists tried to imagine perfect emptiness. A void with no stuff, no energy, no light, no motion. But quantum field theory reveals that even the deepest vacuum is alive with possibility. Fields fill every inch of space, and those fields can never sit perfectly still. They are forced by the laws of nature to jitter, to vibrate, to flicker with little bursts of energy, even when left completely alone. This constant trembling creates tiny, short-lived blips called virtual particles. Virtual particles aren't like the real, lasting particles that make up you, me, or the stars. They're more like temporary sparks, popping into existence and vanishing almost instantly, before anyone can truly catch them. But even though they're brief, they have real effects. They mediate the forces between particles, shift the energies of atoms, and sometimes even create pressures you can measure with the right experiment. Here's an easy way to imagine them. Picture a cartoon where the characters run so fast that their legs become a blur. You know the legs are moving, but you can't track them as individual things. Virtual particles are like that. Too quick and fleeting to be seen directly, but they leave their fingerprints everywhere. So why do these virtual particles matter? They are the secret architects of the universe's forces. For example, when two electrons push away from each other, you might picture tiny balls shooting a force field at each other. But quantum field theory says it's more like this. As the electrons approach, the electron field and the electromagnetic field begin to ripple. a flurry of virtual photons, messengers of the electromagnetic force, burst into existence, carrying momentum and energy between the electrons, then vanish without a trace. This invisible exchange is what we feel as the push or pull of a force. And it's not just electromagnetic forces. Virtual particles mediate every force in nature. Gluons, another kind of virtual particle, hold quarks together in the heart of every atom. Even gravity, the weakest but most far-reaching force, is thought to work this way, although we haven't yet seen the virtual graviton, the mysterious particle that would carry gravity's message. The effects of these invisible architects are everywhere. Take the Casimir effect, a real, measurable force that comes from the virtual particles of the vacuum. Put two metal plates extremely close together in a vacuum, with just a tiny gap between them. You might think nothing would happen, but as we saw before, the fields in the vacuum are still humming with energy. Between the plates, only certain wavelengths of virtual particles can fit, like only certain notes can play between two walls. Outside the plates, the virtual particles can have all kinds of wavelengths. This difference creates an imbalance, pushing the plates gently together, even though there's no air, no light, and nothing visible in between. The vacuum itself, shaped by virtual particles, pushes matter around. Virtual particles are also responsible for effects deep inside atoms. In hydrogen, for example, the presence of virtual particles changes the energy levels of the electron ever so slightly, a shift called the Lamb shift. This tiny difference, predicted by quantum field theory, was later measured in experiments and matched perfectly, another sign that the universe's secret punctuation is real. These virtual effects even stretch to the very edges of our knowledge. Some scientists believe that the energy of all the vacuum fluctuations, this endless jitter of virtual particles, might even shape the universe itself, contributing to the mysterious dark energy that seems to push galaxies apart at the largest scales. The details are still being worked out, but the hints are everywhere. Nothingness is never truly empty, and the smallest changes can echo across the cosmos. But if these particles are always appearing and disappearing, why don't we notice them in daily life? It's because they act on a scale so small and so fast that only with the most delicate experiments can we even glimpse their influence. Most of the time, their effects cancel out, leaving the world looking calm and ordinary. But if you look closer at the tiniest scales, their footprints are everywhere. You might be wondering, are virtual particles real? Or just a trick of the math? It's a deep question. In some ways, they are like little calculations the universe does, trying out different possibilities as it keeps the rules of quantum field theory. But the effects they create, forces, shifts, even changes in the behavior of materials, are very real and can be measured. In the end, nature doesn't care if we call them real or virtual. What matters is that the fields are always active, and their jittery punctuation shapes everything we see. This restless, invisible activity is the reason quantum field theory is so powerful. It explains why forces have the strength they do, why particles behave the way they do, and even why space itself is alive with subtle energy. Without virtual particles, the universe would be silent and dead. No forces, no chemistry, no light, no life. Every interaction, from the smallest push to the largest explosion, is written by their quick, secret movements. In a way, the universe is never done talking. Even in perfect silence, even in the deepest vacuum, the fields keep whispering, humming, and swapping punctuation marks. The world is a conversation without end, and the virtual particles are the breath between every word. So next time you pause and listen to the quiet, know that you're surrounded by an endless, invisible activity. The emptiness is alive. The world is filled with secret punctuation, virtual particles that shape forces, create pressure, and nudge the story forward. Every moment, reality is being written and rewritten, not with ink or light, but with ripples that are too quick to see, too subtle to feel, but absolutely necessary for everything to exist. Quantum field theory invites us to let go of the idea of perfect stillness, to embrace the truth that even nothing is full of motion and meaning. The virtual particles are the hidden architects, building every force and connection we know. They're the silent punctuation that lets the universe speak. The more we learn to listen, the more we understand how much is happening beneath the surface. This is the secret power of the quantum fields. To turn the ordinary into the extraordinary, to make empty space into a canvas for infinite possibility. In the next chapter, we'll see just how far this power can go. The success of quantum field theory isn't just in its wild ideas. It's in its ability to predict, to explain, and to unlock the secrets of the cosmos, with a precision so stunning that it feels like the universe is handing us its grammar book page by page. The invisible world of virtual particles is only the beginning. The real triumphs are just ahead. Are you ready to see what this secret language can really do? Why do things feel heavy? Why does your hand, or a rock, or a planet have weight at all? If the universe is just a web of vibrating fields, why don't things just slide right through each other like ghosts? For most of history, people thought mass and weight were basic, unchanging facts. Objects just had them the way a rock is hard or the sky is blue. But quantum field theory tells a much stranger, deeper story. The weight of everything around you, the heaviness of your body, the earth and the sun, comes not from things themselves, but from a field that quietly fills all of space. And the way we even talk about mass and energy, the very meaning of particles, can shift and stretch depending on how closely we look. Reality is full of surprises, and mass is one of the biggest. Imagine you're at a costume party, and everyone's wearing identical, invisible suits. Most people can move easily across the dance floor, nothing slows them down. But then, a thick, invisible fog rolls in, and suddenly, everyone's steps feel heavy. Their movements are slowed, their path across the floor is harder. This is a little like what happens in the universe. In the earliest moments after the Big Bang, particles zipped around with no resistance, no mass, just pure energy. But then, a mysterious field switched on, the Higgs field, and filled the universe like a thick, invisible fog. As different particles move through this field, some get slowed down a lot and become heavy, while others barely notice it and remain almost weightless. Your mass, and the mass of everything you know, comes from the way particles interact with the Higgs field as they move through space. This Higgs field is everywhere, always switched on, even now in the emptiest parts of space. The Higgs boson, a particle discovered in 2012, is just a ripple in this field, proof that the field is real. When the Higgs field interacts with certain particles, it drags on them, making them behave as if they're heavy. Some particles, like photons, particles of light, can move through the Higgs field without feeling a thing. They stay massless and move at the speed of light forever. Others, like electrons or quarks, get caught by the field and gain mass. The more strongly a particle interacts with the Higgs field, the heavier it becomes. So mass isn't just stuff. It's a relationship, a byproduct of a constant, invisible handshake with this special field. But mass is only part of the story. Quantum field theory also had to deal with something that haunted physicists for years: infinity. When scientists first started using quantum fields to calculate things like the energy of an electron or the strength of forces, they ran into a huge problem. The math often gave answers that were infinite, totally impossible. How could the universe work at all if the numbers just blew up? But rather than give up, they found a clever fix called renormalization. Imagine you're looking at a painting up close, and you see strange, wild brush strokes. If you step back, you see the whole picture. Everything smooths out and makes sense. Renormalization is like adjusting your zoom, focusing only on what's meaningful at the scale you care about, and brushing away the infinities. The universe turns out to be perfectly sensible, as long as you don't try to stare at every little detail all at once. This idea also reveals something magical about the laws of physics. The rules themselves can run or change, depending on how closely you look. When you probe matter at very small distances, or at extremely high energies, the strengths of forces and even the values of masses can shift, just like a word can mean different things in different sentences. This is why physicists talk about running couplings and effective masses. These aren't fixed, eternal numbers, but values that depend on the context, on the energy, on the scale of the dance you're watching. Reality is more flexible than we ever imagined. Even more mysterious, the way particles get their mass, and the way their interactions shift with scale, can sometimes give rise to whole new kinds of matter, emerging from the collective behavior of fields. In certain materials, like superconductors, The quantum fields inside can organize themselves so perfectly that electricity flows with zero resistance. This is a hint that the grammar of quantum field theory isn't just about the fundamental building blocks, but can create new patterns, new meanings, when enough fields come together in the right way. Why does this matter to you? Because every moment you're alive, you're living inside this sea of invisible fields, feeling the drag of the Higgs, experiencing the shifting meanings of energy and mass, and watching the laws of physics play out in real time. Your body, your breath, the weight of the world, all of it is shaped by the way particles and fields interact, by the way the universe hands out mass, and by the way the rules change as you look closer. Quantum field theory asks us to see mass, and even reality itself, as something dynamic, not fixed. Mass is not a number written in stone. It's a process, an effect, a sign that the fields are at work. When you walk, run, or jump, you're negotiating with the Higgs field. When you look at a star or drop a stone, you're watching mass in action. Not as a thing, but as a story, written by the universe's grammar, told in the silent language of fields. Even now, the details of this story are not complete. There are puzzles still unsolved. Why does the Higgs field have the strength it does? Why do some particles hardly notice it, while others get stuck and become incredibly heavy? And how does all this fit together with gravity, the last great mystery, waiting to be woven into the grammar of quantum fields? These are questions physicists are still chasing, because every answer leads to more wonder, more possibilities. But one thing is clear. What you feel as weight, what you experience as something, is the result of a deep, cosmic relationship between invisible fields and the ripples that move through them. Mass is not just a property. It's a dance, a handshake, a conversation. Every step you take, every breath you draw, is a line in that ongoing dialogue. So next time you feel the ground beneath your feet, or lift a heavy object, or even just stand still, remember, you are not just made of stuff. You are shaped by fields, given mass by the Higgs, defined by the rules of quantum grammar, always in motion, always alive. The universe has chosen you as one of its sentences, one of its meanings, and the story is still being written. And as we look further into the world of quantum fields, we'll see just how powerful this story can be. Quantum field theory isn't just an idea. It's the key to understanding why anything exists at all, why anything has mass, and how the universe makes meaning out of motion. It's a reminder that reality is always deeper, richer, and more surprising than we first imagined. The grammar of the cosmos has many rules, many exceptions, and many secrets still left to tell. Are you ready to see just how precisely quantum field theory can predict the world, and where its riddles remain? Let's keep going. The language of the universe has much more to say. The universe's language isn't just beautiful, it's powerful. Imagine a code so precise, so reliable, that every experiment you perform matches its predictions, sometimes to more than 10 decimal places. Quantum field theory is that code. It's not a theory that just kind of works. It's the foundation for almost all of modern physics, a tool that has let us crack open the atom, build computers, map the stars, and even glimpse the edge of reality itself. Yet, even as it shines, it leaves us with riddles that tease the limits of our knowledge, as if the universe is daring us to go further. Let's start with what makes quantum field theory so extraordinary. When scientists first began to test its predictions, they found results that bordered on the miraculous. Take the electron, for example. Physicists can calculate how the electron interacts with other fields using quantum field theory, predicting the electron's magnetic moment, a tiny detail about how the electron spins and wobbles in a magnetic field. The answer from theory matches the measurement from experiments to an accuracy of 1 part in a trillion. This isn't just close. It's so perfect that, if you made the same prediction for the distance from New York to Los Angeles, you'd be correct to within the width of a single human hair. No other idea in science, or maybe even in human history, has ever matched reality so closely. And it's not just electrons. The standard model of particle physics, built from quantum field theory, brings together all the known fundamental particles and their forces except gravity into a single framework. The standard model explains why atoms don't collapse, why the sun shines, why your hand doesn't fall through your coffee mug, and even how the universe makes gold in exploding stars. Every big collider experiment, from the early days of smashing protons to the discovery of the Higgs boson at the Large Hadron Collider, is a triumph of quantum field theory. These experiments don't just confirm old predictions. They constantly test the theory in new, extreme situations, and quantum field theory keeps delivering. It's also everywhere in technology. The screens you're reading this on, the chips in your phone, the lasers in your grocery store scanner, all work because quantum field theory can predict the behavior of electrons in semiconductors and materials. Without these precise calculations, modern life wouldn't just be different, it would be impossible. The very act of making materials that conduct, insulate, or even become superconductors is a kind of practical magic made possible by understanding how quantum fields behave. But every triumph comes with a twist, and quantum field theory is no exception. Even as it gives us answers with breathtaking precision, it also points out the places where our understanding hits a wall. One of the biggest challenges is the hierarchy problem. The Higgs field, as you learned earlier, gives particles mass. But quantum field theory predicts that the mass of the Higgs boson should be much, much heavier than it is, unless something as yet unseen balances out the numbers. It's as if the universe is perfectly fine-tuned, holding onto a secret reason for this delicate balance. Then there's dark matter and dark energy. We know, from looking at galaxies and the universe at large, that most of the matter and energy in the cosmos isn't made from anything we've seen in our labs. Quantum field theory has helped us predict and search for new particles that could be dark matter. But so far, every experiment has come up empty. We know there's something more out there, a missing page in the universe's grammar book, but we haven't found it yet. And gravity, the oldest and most familiar force, remains the trickiest of all. Quantum field theory describes electromagnetism, the strong force, and the weak force with clarity and success, but gravity resists being woven into the quantum tapestry. Attempts to create a quantum field for gravity, the so-called graviton, run into mathematical infinities that won't go away with renormalization. This is the great unfinished chapter of the theory. Physicists dream of a quantum gravity that will tie everything together, maybe through new ideas like string theory or quantum loops, but for now, the code is incomplete. Sometimes, the very math that makes quantum field theory so successful also reveals new mysteries. There are strange effects called anomalies, tiny mismatches between symmetry and reality, that show up as the theory pushes itself to its limits. Some of these anomalies, like those found in the strong force, actually help explain the world, while others seem to point to new physics just out of reach. Each anomaly is like a footnote in the universe's grammar book, reminding us that even the best language has exceptions. Still, the story of quantum field theory is one of ever-increasing accuracy and discovery. When physicists build bigger colliders, probe deeper into matter, or search the sky for new signals, they're really testing the universe's language, seeing if the old grammar still holds or if a new dialect is needed. And every so often, a new discovery appears, like a new word or rule that changes the whole conversation. Perhaps the most exciting part is that quantum field theory isn't finished. Every time we push its predictions to the next level, more decimal places, higher energies, stranger materials, we learn something new and sometimes something unexpected. Quantum field theory is not just a theory about the smallest things. It's a way of asking the universe questions and getting answers so precise they seem like magic. And yet, for all its success, the theory never claims to be the last word. It's a living language, open to new rules and new meanings. Its greatest triumph is not just in how well it works, but in how it keeps challenging us to ask better questions. The unexplained mass of the Higgs, the silence of dark matter, the stubbornness of gravity. These are not failures, but invitations. The universe is saying, "You've learned some of my language. Now try to read the next page." So, when you hear about the discoveries at big science labs, or the search for new particles, or the hunt for the nature of dark matter and energy, know that it's all part of the same journey. Quantum field theory is our most powerful tool, our most accurate map. But every map has blank spaces, territories yet to be explored. As you look back at what we've learned, remember that quantum field theory's greatest achievement is not just in numbers or predictions, but in its ability to keep opening doors. It turns questions into experiments, experiments into answers, and answers into new mysteries. It is both the solution and the starting point, the grammar book and the poem. And through it all, one thing remains true. The universe's language is subtle, deep, and endlessly rich. The more we learn, the more wonder we find. The next time you marvel at a rainbow, a magnet, a supernova, or even your own thoughts, know that quantum field theory is at work beneath it all, whispering the code that keeps the cosmos running. In the final chapter, we'll turn from questions of fact to questions of meaning, and see how learning the universe's language can change the way you see yourself and everything else. The secret language is waiting for you to become fluent. Are you ready to step into the conversation? What if you could see the world through new eyes? Not just as a place filled with things, but as a living language, where every part is connected to every other, woven together by ripples of energy and patterns of possibility. By now, you've heard about fields, ripples, forces, virtual particles, and the astonishing precision of quantum field theory. But the true gift of this secret language isn't just what it tells us about particles or equations. It's how it lets us understand ourselves, our world, and our connection to everything else, in ways more profound and moving than science fiction ever dreamed. Let's step back and remember. The universe, as quantum field theory sees it, is not a place where objects drift through empty space. It is a vast, shimmering web, fields everywhere, at every point, each with its own music, yet all playing together in a grand cosmic orchestra. You are not a thing apart from this web. You are one of its most complex, beautiful songs. A living pattern of fields, a ripple of energy that's conscious, curious, and capable of learning the universe's language. If you close your eyes and picture yourself, you might see a body, a mind, a person sitting in a room. But quantum field theory says, you are a tapestry of fields, woven so tightly that the boundary between you and everything else is more illusion than fact. The fields that make up your body blend with the fields in the air, in the chair, in the starlight coming through your window. Right now, countless quantum fields are passing through you, interacting, exchanging, making you possible in every instant. You are not just in the universe, you are of it. This understanding changes everything. It invites us to look beyond the old idea of separation. The myth of things and emptiness fades away. There is only connection, only conversation, only change. When you move your hand, the fields move with you. When you speak, when you think, when you dream, fields shift and interact. Even your thoughts, those flashes of inspiration, those memories and hopes, depend on fields communicating, patterns arising, vanishing, and arising again. Quantum field theory also shows us that complexity can emerge from simple rules. The same grammar that governs how electrons move or how forces work also creates the astonishing richness of life, of consciousness, of societies, even of stars and galaxies. From simple ripples, new stories are told, new worlds are born. Your mind, your imagination, your creativity. These are not magic, but the high notes of a universal melody played on fields, shaped by the same rules as the smallest particles. This viewpoint isn't just a scientific curiosity. It is a call to humility, wonder, and belonging. When you realize you are made of the same stuff as the sun and the stars, the tree outside your window, the air you breathe, and the light in a distant galaxy, it becomes harder to feel alone or separate. You belong to the universe, and it belongs to you. The fields that give rise to your life are the fields that have danced since the dawn of time. And the beauty of this language is that it's everywhere. Quantum field theory's grammar is not limited to particle physics. The same ideas explain how materials become magnets, how heat moves through a cup of tea, how superconductors let electricity flow with zero resistance. In every one of these cases, new patterns emerge, new particles appear, not as new fundamental fields, but as collective excitations, like new words or dialects in the universal language. Physicists call these quasiparticles. They are not truly fundamental, but they are just as real in the materials where they appear. This is a sign that the universe's language is flexible, creative, endlessly expressive. And then there's emergence, the idea that simple rules, followed by many, can create unexpected, wonderful complexity. Flocks of birds, waves in the ocean, human thoughts, the weather on a stormy night, all can be seen as emergent patterns, higher-level grammar written by the fields and forces of quantum theory. Life itself emerges from the interplay of chemistry, which emerges from the rules of quantum fields. The story never stops. Every pattern gives rise to new stories, new rules, new languages. But even now, the language of the universe is unfinished. New questions keep coming. Is gravity really a field like the others, or does it play by different rules? Could space and time themselves be made of deeper, more mysterious fields, woven together in ways we have yet to imagine? Some physicists are searching for the holographic nature of reality, the idea that everything we see is a projection from deeper laws written on a faraway boundary. Others chase the mysteries of quantum information, seeing the universe not just as fields, but as a giant computation where reality itself is the sum of all possible stories. And so the journey goes on. Every discovery, every equation, every experiment is not just a way to measure the world, but a new sentence in the universe's autobiography. Each new insight, each new piece of grammar we learn, lets us tell more of the story, about stars and atoms, about the very beginnings of time, about ourselves. In this view, you are not a passive observer. You are a participant in the universe's unfolding language. Every time you ask a question, every time you seek to understand, you are sending ripples through the fields, joining the cosmic conversation. Your curiosity is itself a quantum event, a spark that changes the story. This is what makes quantum field theory so profound, so much more than a collection of facts. It is an invitation to fluency, a chance to see the world not as a set of objects, but as a living process, a web of actions and reactions, verbs instead of nouns. The fields don't just make particles. They make meaning, connection, and possibility. So what do you do with this knowledge? Maybe you notice the world a little more carefully. Maybe you feel less alone, knowing that you are, quite literally, a part of everything and everything is a part of you. Maybe you find new wonder in the way sunlight falls on your hand, or how music moves you, or how thoughts spark and change. Every one of those things is a ripple in the universal field, a note in the universe's secret language. And maybe you go further. Maybe you share what you've learned, or dive deeper, exploring the mysteries that remain. Because the best thing about learning the universe's language is that there is always more to say, more to ask, more to discover. As you walk away from this story, remember, you are not separate from the universe. You are a unique phrase in its poem, a ripple in its ocean, a pattern in its infinite web. The language of the universe is not finished. You help write it every day. Once you learn to see the universe's language, even silence feels full of meaning. The world is not made of things, but of possibilities, of stories, ripples, connections. Welcome to the conversation. The universe is speaking, and now you know how to listen.